Okay, today we will talk about some important reactions that take place on the silicate clay minerals or on the surfaces of colloids in the soil. That is the absorption of cations and anions. You remember we talked about the sources of charges last time. So if you have charges on soil colloids, they have to be neutralized. And how are they neutralized? By absorbing cations or anions. In soil, the negative and positive surface charges on the colloids attract and hold a complex swarm of cations and anions. Swarm, a large group close together. Both cations and anions are usually attracted to the same colloid. So that means the same colloid can have positive and negative charges, so it can attract cations and anions at the same time. In temperate region soils, like our soils in Jordan, anions are commonly absorbed in much smaller quantities than cations because these soils generally contain predominantly 2-to-1 type silicate clays in which negative charges predominate. If you remember, we said the positive charges are mostly on humus, 1-to-1 iron aluminum oxides type of clays or colloids. But if you have mostly 2-to-1, if they are the dominant ones, then we will have mostly negative charges. So we talk about cation exchange and cation exchange capacity. In the tropical and semi-tropical areas, where soils are more highly weathered, acid and rich in 1-to-1 clays and iron and aluminum oxide clays, the amount of negative charge on the colloids is not so high and positive charges are more abundant. So it's the opposite of what you find in the temperate regions like our regions. The absorption of these ions by soil colloids greatly affects their biological availability and mobility, thereby influencing both soil fertility and environmental quality. So if these ions are adsorbed on the surfaces of colloids, of course, it will have a lot of effect on their mobility. It will not allow them to leach easily and go down to the groundwater. So, and also it will affect their availability to the plants and microorganisms in the soil. And this, of course, eventually will influence both the soil fertility, how many of these ions are absorbed and stays and they are available to the plants and the microbes, and of course the environmental quality because they will determine how much of these will be leached down to the groundwater. Okay, a negatively charged colloid surface can hold a hydrated cation such as calcium ion. The colloid and the cation are only loosely held together by electrostatic attraction, and the adsorbed ion remains in constant motion near the colloid surface. So, if you have a negatively charged colloid surface, a colloid that has negative charges, it can hold a hydrated cation. An example is calcium. Why do we say hydrated? Because it has water of hydration around it, because these reactions will take place only in salt solution. So you have aqueous system, so they are hydrated cations or ions in general. The colloid and the cation are only loosely held together by electrostatic attraction. This is the attraction between positive and negative charges. So they are not so tight. That's why they are available to plants, available to microorganisms. They are not very tightly held. They are held, but loosely, without too much force. And they are in constant motion near the colloid surface. So they are not like stagnant. sitting there. They move around, but still they are very close to the negative charge, which is on the surface of the colloid. Another hydrated cation from the salt solution, say magnesium, like an example, magnesium, would replace the first ion, which is calcium, freeing the formerly absorbed ion to diffuse out into the salt solution. So if you have calcium adsorbed on the surface of the colloid, magnesium can take the place or replace or exchange calcium. Of course, what will happen to calcium? It will diffuse out, it will leave the surface and go to the salt solution. This process is referred to as cation exchange. If a hydrated anion similarly replaces another hydrated anion at a positively charged colloid site, the process is called anion exchange. So if you have a positive charge on the surface of the colloid and an ion is adsorbed, another anion can take its place. The process is called anion exchange instead of cation exchange. The ions which can be replaced by exchange reactions are said to be exchangeable. That means they are able to be replaced by others. They can be replaced or exchanged by others. So we characterize them as they are exchangeable. They're not permanent there. Some other cations can push them out, take their place, and they will be exchanged. So they are exchangeable cations or anions. This process, which is the cation or anion exchange, and we will be concentrating more on the cation exchange because that's what we have in most soils, especially in our soils. They have certain principles or rules that govern them, that apply to them. I will explain some of them in that chapter you will read in the nature and property of soil. They go into more details. There are more principles and rules, but I will concentrate on 2 or 3 of those that are more important to us. The first is reversibility. It's easily to see what doing from reversibility. The process of cation exchange can be illustrated using a simple reaction in which a hydrogen ion displaces a sodium ion from its adsorbed state on a colloid surface. So we have a micelle. A micelle, we can say also a particle or crystal of any of that. Means if we say crystal, of course, we're talking about the silicate clays. But if we are organic, it's micelle. It's a particle of that colloid. So we have a sodium adsorbed on that micelle. Hydrogen can take the place of sodium. And so what we end up with the micelle with hydrogen on the exchange site, and sodium is pushed out or diffused out to the salt solution. The reaction takes place rapidly, and as shown by the double arrows, as you can see, the reaction is reversible, so it can go either way in each direction. It will go to the left if sodium is added to the system. This reversibility is a fundamental principle of cation exchange. So you add more sodium here, it will push the reaction back again, and that sodium will get back to the micelle. Hydrogen will be loose in the salt solution. Another important principle or property of this cation exchange reaction is charge equivalence. This is extremely important. Concentrate, and you should understand it very well. It's easy, but concentrate to understand this principle very, very well. What do we mean by charge equivalence? Another basic principle of cation exchange reactions is that the exchange is chemically equivalent. What do we mean by chemically equivalent? That is, it takes place on a charge for charge basis, not an element for an element, charge for charge basis. We have negative charges that attract cations, and so the amount of those cations will be having enough positive charges to neutralize these negative charges, regardless what are those ions. So we will keep this in mind as we talk about this important principle. Although one hydrogen ion exchanged with one sodium ion in the reaction just shown, it would require two singly charged hydrogen ions to exchange with or replace one divalent calcium ion. So if you have monovalent taking the place of monovalent, that's one charge for one charge. So that's 1 for 1. But if you have calcium, okay, and it's absorbed and you are going to replace it with hydrogen, calcium carries two positive charges, which means these two positive charges are neutralizing two negative charges on the colloid surface. So you need two hydrogen to give you two positive charges to replace calcium. So this is what we mean, charge for charge, two charges to replace two charges. If one cation carries these two charges, then you need two monovalent cations to replace that same cation. If the reaction is reversed, one calcium ion will replace two hydrogen ions. So if you have two hydrogen ions adsorbed on the surface of the colloid, one calcium, because it carries two charges, will replace these two hydrogen. In other words, two charges from one cation species replace two charges from the other, regardless what it is. So if it's divalent, it's providing two charges, so it will replace two monovalent. Two monovalents are needed to replace one cation which carries two positive charges. So here is the diagram. My cell with a calcium ion adsorbed to it. You need two hydrogen ions. Each one of them carries one positive valence. So the micelle will have the two hydrogen. Calcium is pushed to the solution. So two charges took two charges. Two charges replaced two charges. Not an element. If it was element, it would be 1 for 1. No. Two hydrogens were needed to replace one calcium because this one carries two charges, and each one of those carries one charge. Another important principle of these reactions is the cation selectivity. Up to now, we have assumed that both cation species taking part in the exchange reactions are held with equal tenacity by the colloid and therefore have an equal chance of displacing each other. Tenacity force, the force of attraction, how strongly it's adsorbed. So not all cations are held by the colloids by the same force. So some of them are held stronger than others. So that's what's meant by the cation selectivity. Not all of them are adsorbed by the same force. In reality, some cations are held much more tightly than others, and so are less likely to be displaced from the colloids. If they are adsorbed more strongly, it will not be easy to replace them by others. In general, how is this explained and why? What are the reasons for these differences? In general, the higher the charge and the smaller the hydrated radius of the cation, the more strongly it will adsorb to the colloid. Naturally, if it has higher charge, so if you compare a divalent to a monovalent, of course, remember the attraction between charges or negative and positive charges. Okay, you know it from Coulomb law that the higher the amount of charge, the stronger is the attraction. So a divalent has two charges will be attracted more strongly to the surface that's negatively charged than a monovalent, which carries one charge. And a trivalent, like say aluminum, will be even held stronger than divalent and monovalent. And then the second character or reason for that is the hydrated size of the cations. The smaller the hydrated the size, that means that charge that it carries is distributed over a smaller sphere, so the density of the charge will be higher, so the attraction will be higher. So the order of strength of absorption of the most common cations in soils: aluminum, trivalent, stronger than calcium, stronger than magnesium. Then in magnesium and, sorry, calcium, magnesium here, they're both divalent. Why calcium is stronger it's held stronger than magnesium? Remember, that is because of the size of hydration. That means this has smaller size of hydration, so the concentration of the charge will be, or the density will be higher, so it's attracted stronger to the negatively charged surface of colloids. And so these, remember, trivalent, divalent, we know the difference between these two. All of them stronger than potassium monovalent. And potassium equals to ammonium, they are pretty much the same. And the least absorbed is sodium because it has very large, compared to potassium and ammonium, very large hydrated size, which makes the density of the charge on that sphere very low, so the absorption strength is also low. Okay, we will move into another aspect of the cation exchange reactions. Previously, we dealt qualitatively with exchange reactions. We described them in a qualitative way. We talked about qualitative characteristics. We now turn to a consideration of the quantitative cation exchange capacity, CEC, cation exchange capacity. Remember, you cannot use abbreviations only after you use the full expression, cation exchange capacity. You write it down first, then between parentheses, you can use symbols to represent it. This property is defined simply as the sum total of the exchangeable cations that a soil can absorb. So you add up sum total, add all the exchangeable cations that are on the colloidal surfaces, add them together, that will give you the cation exchange capacity, the amount that it can hold. Means of expression, how do we express it? What kind of unit we talk about? That's what we mean by expression in this case. What kind of units you use to indicate it, to talk about it? The cation exchange capacity is expressed as the number of moles of positive charge adsorbed per unit mass. So moles of charges and unit mass. Of course, now we'll go more detailed, define more in numbers, in units. In order to be able to deal with whole numbers of a convenient size, usually CEC values are reported in centimoles of charge per kilogram of soil. So instead of using the mole large unit, we use centimole, which is smaller unit, so that the numbers that when we measure them will be large and convenient. That's what it's just a matter of convenience. Of course, we can use mole and still be the same exact amount, but to have numbers that are easy to deal with, convenient size, so the scientists decided to use the centimole, 1/100 of the mole per kilogram of soil. Some publications still use the older unit, which is the milliequivalent per 100 gram of soil. If you go back in probably 2 decades or more, all the units that were used to express or talk about the CEC were in milliequivalents per 100 gram of soil, milliequivalents per 100 gram of soil, instead of centimole of charge per kilogram. But these two units in number are the same. So if you give this value and this value in number, the value of them did not change. And this is very good, so that when you compare old literature that talked about the CEC in milliequivalent per 100 gram, they will be the same numbers. We can compare them with recent literature, with recent research that uses the centimole charge per kilogram of soil. Okay, let's go into now more detail, how we express, how we calculate. Again, concentrate, it's easy, but you need to concentrate on how we do the calculations, how we do the moving from one unit to another. Real simple, but you have to concentrate on it as we go through the examples. A particular soil may have a CEC of 15 centimole of charge per kilogram. Remember, we didn't say centimole of sodium, of magnesium, of calcium, of aluminum. Remember, charges. Remember when we said the equivalent characteristic of it, that means charge for charge. So all our talk always will be in charges. This is how we can change from one element to another without having any problem. Think of that principle always. 15 centimole of charge per kilogram of soil, indicating that 1 kilogram of the soil can hold 15 centimole of charge of hydrogen ions. If the hydrogen ion is the one that's absorbed, so it will have 15 centimole, remember, of charge. But these charges are provided by hydrogen, for example, and can exchange this number of charges from hydrogen ions for the same number of charges from any other cation. So it doesn't matter what the cation, remember, the same number of charges. This means of expression, the way we indicate the units we use, emphasizes that exchange reaction take place on a charge for charge, not an ion for an ion, just like we said earlier. Remember this important principle. The exchange reactions take place on a charge for charge, not an ion for an ion basis. 1 mole of any atom, molecule, or charge is defined as 6.02 times 10 to the 23, which is Avogadro's number of atoms, molecules, or charges. If you remember, when in the undergraduate courses, I used to give you a few lectures on chemistry, and one of the things we concentrated on defining mole, and we said the mole is the counting unit of chemistry. So if we say 1 mole of atoms, 1 mole of molecules, 1 mole of charge, it's always this number, 6.02 times 10 to the 23, which is Avogadro's number. So if you have 1 mole of atoms, that means you have Avogadro numbers of atoms. If you have 1 mole of molecules, you have Avogadro's number of molecules. If you have 1 mole of charges, you have Avogadro number of charges. So no matter what you count, a mole of that thing, the entity you're talking about, will be in number, Avogadro number, which is this huge number. Thus, 6.02 times 10 to the 23 negative charges associated with the soil colloidal complex would attract 1 mole of positive charge from the adsorbed cations, such as calcium, magnesium, and hydrogen. So if you have 1 mole of negative charges on the soil colloids, okay, so they have to be neutralized. They will attract 1 mole positive charges, charge for charge. 1 mole negative charges, will require 1 mole of positive charges, regardless where it comes from. Calcium, magnesium, hydrogen, combination of these, combination with other cations, it does not make any difference. Charge for charge. Okay, using the mole concept, it's easy to relate the mole charges to the mass of ions or compounds involved in cation or anion exchange. Again, concentrate. In reality and in life, we don't deal with ions. We cannot say buy or bring into the field or to the laboratory ions. You never do that. Ions are part of compounds. So we will first talk about the calculations on ion basis, and then later, the last step, we will move on to the compounds they come from. So consider, for example, the exchange that takes place when adsorbed sodium ions in an alkaline arid region soil are replaced by hydrogen ions. So now we have sodium on the micelle, just like we have shown earlier, it will be replaced by hydrogen. So the micelle will have hydrogen and sodium is being diffused out to the salt solution. Now we will take numbers. If 2 centimole of charge of adsorbed sodium, remember, we're saying 2 centimole of charge of adsorbed sodium. We didn't say 2 centimole of sodium. 2 centimole of charge of adsorbed sodium. That means we have 2 centimole of charge. The source of them is sodium. Okay, concentrate. So that if we have then the example here, 2 centimole of charge of adsorbed sodium ions per kilogram of soil, they were replaced by hydrogen ions in this reaction that we see here. Okay, the question is, how many grams of sodium ions would be replaced? So we're gonna change and move on one step from the centimole of charge supplied by that ion to the mass of that ion that gave us that many centimole of charges. Since the sodium ion is singly charged, it has 1 positive charge, so it's singly, it's a monovalent, the mass of sodium needed to provide 1 mole of charge, 1 mole of charge is the gram atomic weight of sodium, or 23 grams. Remember, again, if you remember and you go back to your notes in the undergraduate or in your chemistry that you studied, 1 mole of an element, sodium is an element, 1 mole of an element, that means it is the atomic weight of that element. 1 mole of it in grams is the atomic weight of that element. So sodium, the atomic weight of it is 23. So if we take 23 grams of sodium, that will be 1 mole of sodium. So that will be an Avogadro number of sodium atoms. And it will be the same as sodium ions, because when you lose an electron, it does not change the mass at all. It's the same mass. So we can consider the mass of Na plus and Na the same. So that means the mass of sodium ions is, if we have 1 mole of sodium ions, the mass of it will be 23 grams, and the number of these ions or atoms that carry a charge will be Avogadro number. Okay, so keep this in mind. Easy, but concentrate. So the mass providing 1 centimole of charge is 1 over 100 of this amount, or 0.23 gram. So remember, we said 1 mole of sodium, which equals 23 grams, it provided 1 mole of charge. Na plus, remember we said the same mass of Na plus or Na the same. So we will assume for our purpose, it will be the mass sodium ions. So 1 mole of sodium ion, which is Avogadro number, which the mass of it is 23 grams, will give us 1 mole of charge. But I want centimole of charge. So that's 1/100 of that amount. So we divide the mass over 100. So 23 over 100 will give us 0.23 gram to give us 1 centimole of charge. Thus, the mass of the 2 centimole charge of sodium replaced from 1 kilogram of soil is 2 centimole, that's the example, 2 centimole of charge of sodium per kilogram. Each one of these centimoles we already decided and calculated, it weighs 0.23 gram. So the 2 centimole, 2 times 0.23 gram will give us 0.46 grams of sodium ions per kilogram of soil. So that's an answer to the what is the mass of sodium that was replaced. So it is 0.46 gram. The 0.46 gram sodium would be replaced by only 0.02 grams of hydrogen. If they want to replace it back again, the sodium with hydrogen. Sorry. Okay, the atomic weight of hydrogen is 1. So the 1 gram will give us 1 mole of charge from hydrogen. The centimole of hydrogen will be 1 divided by 100.01. So the 2 centimole will be 0.01, like we did with 0.23. 0.01 times 2 will be 0.02 gram. So that's why we say the centimole is the same of charge, did not change. It's that 2 centimole of charge. Remember, we needed 0.46 gram of sodium to give us those 2 centimole of charge, and we needed 0.02 gram of hydrogen to give us the same 2 centimole of charge. That's why we don't say element per element. It's mole of charge, centimole of charge for charge. And that mass of any element will depend on its atomic weight. So this is very variable. This is constant, 2 centimole of charge. Another example is the replacement of hydrogen ions, which is the last aspect of it. Because again, like we said, you cannot find ions alone. You cannot have them individually in life. They have to be part of a compound. So we're going to find compounds that will provide the ions we need. This is the last example we will talk about. Another example is the replacement of hydrogen ions when lime, which is calcium hydroxide, is added to an acid soil. So you have 2 hydrogens on a micelle. Okay, calcium OH2 is needed to replace. We don't need the compound to replace. The compound, this will be a source of calcium. When you put this in water, it will dissolve into calcium plus 2 hydroxide ions. So the calcium that's released after the dissolving this compound, it will be the one taking the place of the 2 hydrogen. So 1 calcium took the place of the 2 hydrogen. Remember, charge for charge. 2 charges needs a divalent ion with 2 charges to replace them. And then of course you have water. Okay, the hydrogen with the OH formed water. Assume, okay, we'll go into numbers again, like we did with the centimole of charges a minute ago. This is the same, but we will go into compounds. Assume, that's an assumption, an example just to work with. 4 centimole of charge of hydrogen per kilogram soil is replaced by the calcium hydroxide, which reacts with the soil, with the acid soil. Remember, this compound does not replace hydrogen. This compound is a source of calcium. Calcium, the cation, is the one from this compound that will replace the hydrogen. Okay, since the calcium ion in each molecule of calcium hydroxide has 2 positive charges, the mass of calcium hydroxide needed to replace 1 mole of charge from the hydrogen ions is only 1/2 of the gram molecular weight of this compound, or 74/2, which is equal 37 grams. So I'll repeat it in a different way and slowly again. So if you take this compound, calcium hydroxide, calculate the molecular weight of it, you will find it's 74. So 74 is the molecular weight. If I take a molecular weight, which is 74 grams, it will give us 1 mole of this molecule. It will give us 1 mole of calcium ions. 1 mole of calcium ions. But remember, each calcium ion carries 2 charges. So that 1 mole will give us 2 moles of positive charges. 1 mole of molecules, Avogadro number of molecules. Each one of those molecules will give us also 1 Ca2 plus. Ca2 plus, each one of them carries 2 positive charges. So if I count the number of positive charges, 1 mole of this will give me 2 moles of positive charges coming from calcium. But I want only 1 mole of charge. So I take only half of this. That's why we divided over half. So half a mole will give us 1 mole of positive charges coming from calcium. So that is 37 grams. So back to our question. To replace 1 centimole, since we're dealing always with centimole for the CEC, centimole of charge, we need 37/100. This 37 grams will give us 1 mole of positive charges. Okay, I want 1 centimole positive charges. Divide this by 100. So we divide it by 100 will give us 0.37 grams. The mass of CaOH2 needed to replace 4 centimole of charge of hydrogen per kilogram soil. Remember, just like we did in the other examples, each centimole weighs 0.37 grams. If we need to replace 4 centimoles, we multiply the 4 by 0.37, which is the mass for each centimole, will give us 1.48 grams of calcium hydroxide per kilogram soil. So go over this again slowly, do the calculations on your own, and repeat it how many times you need to repeat it. Write down, calculate, use paper and pencil or pen. And if you have any problems, anything, you can ask and we can discuss it in any way you want. Okay? And best of luck.